I'm going to share my 20-year journey with you, a quest to find a solution to heterogeneous computing, a problem that today has become a global crisis. Hardware has become the Wild West. The only way software can keep up is to rewrite the exact same application again and again for every new hardware device. But by the time the rewrite is finished, the hardware is already obsolete. Let's look at how computing hardware performance has changed over time. In the sequential era, hardware performance came from increasing clock frequencies. Then we hit an inflection point, and the parallel era began. Hardware performance came from increasingly parallel hardware. Then we hit an inflection point, and the heterogeneous era began. Hardware performance now comes from increasingly specialized accelerators. There are no more inflection points. The heterogeneous hardware era will last forever. This is the story of the potential performance that hardware makes available to your software applications. But the software applications you have do not automatically benefit from this hardware potential. You have to rewrite your code to be parallel. You have to rewrite your code to be heterogeneous. By default, your code runs sequentially. This leads to an efficiency gap because your software applications are not using hardware to its full potential. This is waste, wasted energy, wasted money, wasted potential. What is the difference in performance between an efficient, optimized application and an inefficient, unoptimized application? John Hennessy, chairman of Alphabet, in his Turing Award lecture in 2017, showed that an optimized program can run 63,000 times faster than an unoptimized program on a CPU. An unoptimized program is 0.002% efficient. This number is a lot bigger when we look at modern GPUs because the gap has only grown. So why isn't everyone optimizing their programs? Software complexity is what determines project duration and cost. To get that performance, experts have to rewrite every application for every hardware device. And today, we get new application devices faster than we can write software. Performance tuning is hard to do, error-prone, and manual. The cost-benefit of closing the efficiency gap doesn't work out. So what's the effect on the market? The market has separated into the haves and have-nots. Some market verticals can justify the expense for expert developers to close that gap. The rest of the market faces stagnant performance and inefficiency for the rest of time, unless we do something. My quest to fix this problem began in 1999. Imagine an awkward teenager in his basement room reading books about the Manhattan Project and Silicon Valley, soldering electronics, and getting electrocuted. And in 2001, growing up to be an awkward university student, studying physics by day and installing Unix variants by night. Who in 2002 bought an Itanium server off eBay. The Itanium was supposed to be the future of computing. It offered great hardware performance potential. But software applications did not get that performance because it was too hard to program. This is when I learned about the hardware-software mismatch. Itanium was the canary in the coal mine. Donald Knuth, a famous computer scientist, said at the time that it is impossible to get the performance from Itanium. I was fascinated. In 2004, the sequential era ended because hardware had reached physical limits. The dawn of the parallel era was not celebrated. Nobody wanted it, but the industry had no choice. Even today, software engineers are trained to avoid writing parallel code at all cost and just accept the efficiency gap. Here are a few perspectives on why that is. Tim Mattson, the Intel engineer who created the popular software frameworks we use for parallel programming, told us at the time that software is not ready to be parallel. John Hennessy told us that making parallel programming easy is one of the hardest problems in computer science. He said at the time he would be in a panic if he were in industry. Donald Knuth tells us he doesn't understand parallel programming well enough to teach it to others. He says we should listen to someone else on matters of parallel programming. Here are the pioneers of computing telling you that it's too complicated to write software for parallel computers. So what is the solution? The way to tame complexity is to make parallel programming sequential. We want a system that can take sequential code and automatically transform it into a parallel program. This would permanently close the efficiency gap. It would tame complexity. It would have saved Itanium. But nobody can figure out how to do it. In 2004, in a smoky bar on campus, my mentor and Professor Bob Kent inspired me to become the person who could figure out automatic parallelization. But who am I to figure it out? This problem has stumped the world's leading computer scientist. I had not even written a single parallel program yet, but it became my life's mission. I transferred to the University of Toronto and restarted my education. Every course, project, and job was in some way related to my new mission. I took the hardest math and computer science courses and learned AI from the pioneers. And during my studies, the parallel era gave way to the heterogeneous era, so I pivoted in 2008 to work on the heterogeneous computing problem. I wondered what software would be like after hardware performance potential stopped. And at the end of my undergraduate studies, I understood what it took to automatically parallelize programs. We need a system that can analyze a program and get an upper bound on its execution time, and understand how every part of the program depends on every other part. Then we can automatically break apart a program for parallel execution. But I also learned something else. It's mathematically impossible to do it. Dennis Ritchie said in 1967 that it's impossible to analyze a program and get a bound on its running time. He created Unix and C, upon which all of today's computing infrastructure is built. The impossibility results limit how we build software and infrastructure, and tells us we cannot automatically parallelize programs. Finding all dependencies in a program is also undecidable, which is a computer science term that means impossible. But what does a program look like when it's impossible to analyze? Here's a program with a bug. It takes an exponential amount of time to execute because of a mistake with loop indices. No compiler or tool will find this bug. Code cannot be analyzed. It's a fundamental law of computing. So at graduation, I had my answer. Automatic parallelization is mathematically impossible, and the efficiency gap is a permanent feature of the technology industry. I had to decide what to do with my life's mission. I couldn't accept that automatic parallelization was impossible. Imagine telling your friends at graduation that you're going to give up your career, go into the mountains, and look for a Yeti. This is exactly how you sound if you want to solve automatic parallelization, and that is exactly what I did. In 2014, I started a company, YetiWare, to pay bills with consulting as I continued my quest. Every day for years, I carried papers and books from my apartment to Robarts Library at the University of Toronto, where I read every paper and book I could find on parallel programming to learn and look for a solution. And when I got stuck, I audited graduate courses. But no matter how hard I tried, I could not find a solution. I needed to collaborate with others. I was missing half of the equation. I needed to understand the hardware perspective. I started to collaborate with AMD to learn more about GPU architecture and the future of silicon. I was a visitor to the Fields Institute for Mathematical Research, where I studied the theoretical limits of parallel computing. I was invited to join the OpenCL working group, where I learned directly from the people who created heterogeneous computing. Paul Chow, a computer architect who contributed to RISC processor designs at Stanford with John Hennessy in the 80s and an expert in reconfigurable silicon, helped me understand the low-level hardware details. But nothing worked. I felt like it was time to give up, because maybe it really is impossible to close the efficiency gap. But then I figured it out. Look at the software stack. We have applications. These are built on top of libraries and frameworks, written in programming languages, with system software like the operating system and compiler that abstract the hardware, that targets a low-level interface to physical hardware devices. But underneath all of that, at the very foundation, is a computing model. The entire IT economy, everything, is built upon a theoretical model of software. This model was created by two pioneers. Alan Turing in 1936 created how software works, and John von Neumann in 1945 designed how software works with memory. Alan Turing proved that software is fundamentally unpredictable and is mathematically impossible to build a tool that will determine what a program will do. including its execution time. So we cannot analyze programs. Think about all of our problems today. How can we solve them all at once? If we can analyze programs to predict what they will do before we run them, we can solve these problems. Today, everyone thinks AI can solve these problems, but AI has mathematical handcuffs imposed by Turing's software model, so the best AI can do is guess. But what happens if we create a new model from the ground up so that software is analyzable and predictable? AI could see the inefficiencies and close the gaps automatically and transparently. Had anyone thought of this? Yes, D.A. Turner said that at the beginning of computing there was a fork in the road, and we chose a software model that could not be analyzed. What if we went the other way? Dennis Ritchie referenced Turing's work when he said, "We cannot predict the runtime of software." But then he said we can do it for many useful programs. In his unpublished PhD thesis, Ritchie tried to restrict the programming model so that programs can be analyzed. Ritchie was too early. He needed theoretical results from the 70s, 80s, and 90s. He needed the industry experience that told us what restrictions to make. This was my aha moment. Software engineers already write style guidelines to restrict how they write code. We need to design a model based on these restrictions. This makes software predictable and analyzable. But what about complexity? John Backus created high-level programming languages, and in his Turing Award paper in 1978, he argued that the von Neumann model is the root cause of software complexity. He argued that to unlock new computer architectures, we need a new theoretical foundation for software. This is like saying we need to invent nuclear physics as the first step of the Manhattan Project of automatic parallelization. So that is what I did. I created a new theoretical foundation for software named after the University of Toronto. Then I redesigned the entire compute stack, from the hardware interface up to applications, based on this new foundation, with an adaptive hardware interface for plug-and-play heterogeneity that learns how hardware works as programs execute, with system software that automatically adapts to runtime behavior and can rewrite its own code in a way that is mathematically correct, no hallucinating LLMs, with a universal assembly language that can target any hardware that exists today or that ever will. Finally, a programming language so radically simple that a high school student can get the same performance as a team of NVIDIA engineers. This realizes Backus's dream of taming complexity. But does it really work? In the Manhattan Project, Enrico Fermi built a nuclear pile to prove the theory matched reality. Together with Shane Peeler, we have built enough of the stack to prove the theory works. I am pasting the exponential bug program into the source code window. The system instantly analyzed it and found the bug. Look at this program. We have a closed form for the upper bound on the running time. We have the dependencies of the entire program. This is automatic parallelization targeting a simulated processor. The system broke the program apart and generated a static execution schedule. This schedule is what would have saved Itanium. Every computer scientist is trained that what you have just seen is mathematically impossible. And for a computer scientist, this is like watching an atom being split. Donald Knuth said we need to listen to the experts on parallelism. We need to find the right person to critique and verify this result. Maurice Herlihy wrote the book on parallel programming. He won the Dijkstra Prize 3 times, and modern distributed and parallel systems are based on his theories. Maurice joined my quest in 2019.
Hello, everyone. I'm Maurice Herlihy, online professor of computer science at Brown University. My research concerns concurrency in parallel and distributed systems. I've been involved from the very start with ideas such as linearizability, weight-free and lock-free synchronization, hardware transactional memory, and other ways to impose order on complex concurrent systems. Now I'm working with AJ and the YetiWare team because they're the first people I've met who actually seem like they could automate away my job. Today, concurrency is hard. People are notoriously bad at writing and reasoning about concurrent programs, especially on today's specialized architectures. YetiWare's vision is that you should be able to simply state what you want done and let your compiler and runtime work together to figure out how to decompose your program into parts that can be efficiently and correctly run in parallel on your target architecture. YetiWare's insight is that if your program is structured from the very start, so you can detect how different parts do and do not depend on each other, then with modern compilers /runtime /machine learning technology, automatic, efficient, and concurrent parallelism for specialized architectures is within reach.
Today, the world is in crisis because inefficient software is burning up the planet. We are shoveling coal, applications based on the old inefficient software model, into GPU data centers. The industry is focused on improving data center efficiency, but they are not addressing the root cause of the problem. It's like addressing pollution by changing the light bulbs of a coal plant to LED. Itanium is in the graveyard of computer architectures because programmers could not realize its performance. But today's AI accelerators are harder to program than Itanium. We must learn the lesson that software performance matters. I am now joined on my mission by a group of advisors who have created the technology that powers our world, including Bjarne Stroustrup, creator of C++, and Tim Mattson, creator of OpenCL and OpenMP. These advisors have challenged me on every technical decision, every claim, to help me build this company and technology. We have held ourselves to the highest scientific standards. With a new computing model and a platform based upon its principles, we can close the efficiency gap forever so that software will get performance from hardware no matter how it changes. We can now address the root cause of software complexity. And all market verticals can get the full value out of their existing and future infrastructure. We are making you a promise that you need to re-platform your applications one final time, and for the next 100 years, you will accumulate the benefit of technology innovation without rewriting your code. This promise has been made before. In the 1960s, IBM, led by Fred Brooks, created the mainframe, and to this day, it runs software written in the 60s. Nicholas Donofrio was IBM's Executive Vice President of Innovation and Technology. He led the IBM mainframe business and guided IBM through radical technology changes with the innovation mindset, if nothing changes, nothing changes. He has driven the technological transformations that power modern business. Now, he's helping to shape YetiWare's commercial strategy as we build this platform for the world's most critical enterprise environments so that they can realize the cost efficiency of durable software combined with the performance potential of the heterogeneous era. The research phase of our work is done. We have proven the theory works in reality. We are now building the full platform to be operational on physical hardware at scale. The winter of software inefficiency is here, and Yetis thrive in the winter. Join the revolution.